Welcome to the video. I'm very pleased to say that in the last 3 or 4 months, Dr. EMC channel has grown substantially and it's now nearing its first 1000 subscriber milestone. I would like to celebrate this by making a video about one of the fundamental things that got this channel started on first place, and I would also like to thank everyone who's been there for the last 2 years. Maybe trying to be better at their job, or just trying to learn something new, find a job, or simply listening to me talk for half an hour. I appreciate each and every one of you. Big thank you. So let's now talk about EMC and about how to pass the damn test on the first attempt. And whilst I understand that this may not be the easiest job in the world, I truly believe that any engineer is capable of designing a really good product that can actually do that if they just follow those simple rules. And the rule number 1 is that you should really master the electromagnetic wave propagation in your product. And this is really the key, because you are supposed to be the technical authority on the project and on the circuit that you are designing, so you should really know everything about it. And I am continuously getting frustrated with people giving me answers that when something goes wrong, like, well, my PM asked me to do this, or my PM asked me to do that. You should never let non-technical person make technical decisions that relate to EMC or electrical safety. Full stop. However, in order for you to truly take ownership of the project and be the technical guru that everyone looks up to, you really need to understand the basics of electromagnetic wave propagation, and there's just no other way around it. So let's do a quick recap. So one of the most fundamental things to understand is that electromagnetic waves are actually all around us. And whilst we like to deal with so-called intentional electromagnetic radiation, otherwise called signal, we also have to deal with unintentional electromagnetic wave radiation that is called noise. And in fact, someone else's signal would be noise to us, and noise to our signal, and our signal will be noise to their signal. So this is all kind of subjective, how you see it. But really, electromagnetic waves are all the same, and the way they work is that the time-varying magnetic fields create time-varying electric fields, which allows electromagnetic waves to propagate in vacuum. Whereas on your circuit board, you will create those electromagnetic waves, and they will start propagating outwards by following the force of Lorentz oscillation model. And you can see it here, where the electron mass is getting accelerated and in the direction of magnetic field B. So this is what allows electromagnetic wave to radiate and be received to and from antennas. In the actual fact, this process allows the universe to expand outwards, and if you ever feel insignificant in life, you should know that your poorly designed circuit allows universe to expand at a faster rate. Anyway, going back to physics, really what all this electromagnetic wave propagation follows is the Maxwell's equations, which are shown on this screen here, and they follow the rules of divergence and curl and gradient, which is basically a del operator of a function. So let's do a quick recap of electromagnetic wave propagation theory. And in the example here, you can see that electric fields are orthogonal to magnetic flux in an electromagnetic wave. And that effectively propagates in a direction of the so-called pointing vector. And the pointing vector shows that the E field is a cross product of magnetic flux and also multiplied by 1 over permittivity of free space, which is the material response, and that effectively adds up to about impedance of 377 ohm in air. So if we analyze the electromagnetic wave propagation from the point of view of Maxwell's equations, we see that the del operator of electric field is the derivative of magnetic flux with respect to time, and the del operator of magnetic field is the derivative of electric flux over time. And all of those are vector quantities in three-dimensional space, meaning that a del operator is effectively a derivative of x over time, then derivative of y over time, and derivative of z over time, and this is a column vector. Whilst the propagation of electric fields is entirely dependent on magnetic flux, the propagation of magnetic fields is dependent on electric flux plus J, and J is the surface current density inside a conductor, and it is characterized as current over surface area. And that brings us to the next point, and that is that when there is an alternating current inside a wire, then there's going to be a magnetic field all around it, and we can show it as such. When we have, let's say, a conductor and there is a current, then this is I, then you will have magnetic fields originating around it like this. So this is effectively the Beard-Savart law. So the Beard-Savart law tells us that when there is an alternating current inside a conductor, there will be magnetic fields originating around it, and they will be orthogonal to the direction of this alternating current, and this magnetic flux can be characterized as permittivity of free space over 4 pi and proportional to derivative of length of this conductor times the observation distance to the point B, because we're measuring this magnetic flux at a specific point, and over this distance squared. And this is how an electromagnetic wave originates from an antenna. So, and this is how dipole antennas really work, is that when you pass the current through the dipole antenna, it starts to create magnetic fields all around it, and then those magnetic fields create electric fields, and the electromagnetic wave is propagating outwards by following the Fresnel equation, which is shown here. This is the path loss in assuming the air, so assuming that we are on Earth. And what you should also know from Fresnel's equations is that electromagnetic waves do not propagate in straight lines. Instead, they tend to form beams, which are sphere-like bursts of energy, and they are shown here, and they follow specific zones. And those zones are what defines the near and far fields of electromagnetic wave propagation, where immediately at the source you have a reactive near field, and then as you expand outwards, as the electromagnetic wave expands outwards, it becomes radiating near field, and eventually at a distance that is a wavelength over 2 pi approximately, the electromagnetic wave becomes far field, meaning that its H and E field wave impedance equalizes, and that allows it to propagate forward with constant path loss. What is importance of this for an EMC engineer is, first of all, to know where to put your antenna so that it's always in a far field, because we don't want to measure electromagnetic wave radiation in the near field. And secondly, it also to know that the radiating near field can be quite unpredictable because of different polarization of electromagnetic waves, so that where you have electric field as dominant, it could be as dominant as 80%. So if you're measuring with antennas that is polarized in magnetic field, then you're not gonna see anything. But if you just turn its orientation a little bit, you will suddenly see a lot. But that doesn't necessarily mean that it will actually constitute itself as a lot of radiation in a far field, because by the time it gets to the far field, those H and E fields will equalize themselves, and quite possibly it's not going to be much concern at all. So that's kind of what you need to know about that. And when we want to test the electric and magnetic fields, we use those antennas, and we use electric and magnetic field probes, and like I said, and then we put them inside radiated emissions test house, so anechoic chamber, meaning that inside such chamber there is no interference from outer world and there isn't any reflections. So this is a purpose-built chamber designed for this kind of testing. Now this is about as much as you really need to know about electromagnetic wave propagation, and if you want to dig deeper, you can study also constitutive relationships that relate Maxwell's equations of electromagnetic waves to the real world, so that you can apply, for example, shielding, which allows you to reflect electric energy and absorb magnetic energy. So this is what you tend to do when you design shields, and as well you should follow some rules in terms of you are allowed to have some empty space inside the shield, or some holes inside the shield, but as long as those holes are very small in comparison to the wavelength of the fundamental frequency, they're not going to cause any issue. And also your shield should be of sufficient thickness to absorb magnetic fields, otherwise the magnetic fields will simply propagate straight through it and create electric fields all over again, so your shield will not work. So that's enough about that, and once you truly understand and can master the electromagnetic flow of energy on your circuit board or inside your product, then the next thing you should do is that you really need to understand the requirements for your product. And this is also really important, because they are really not the same depending on the operational environment. For example, if you would be designing a military-grade circuit, you would have to follow MIL 461 standards, which can be extremely stringent, and they would require you to test it for immunity up to 300 volts per meter and things like that. Those kind of tests are completely irrelevant for commercial grade products, where we usually only test up to 3 volts per meter, or sometimes 10 volts per meter, but very rarely. So it is completely unnecessary to provide such a shielding as you would for military grade products in a commercial grade product, and you can save a lot of cost. So the point here is that there are many different types of EMC, which could be automotive EMC, domestic or commercial EMC, medical EMC, the aforementioned military EMC, or railway EMC, and there are really different types of requirements for each and one of them that prescribe different types of testing. So if you don't understand what kind of environmental testing you would likely to do when you finish the design of your product, then how can you actually design it to meet those specifications? Therefore, it's extremely important that you know those things in advance and you know what to prepare your product for, which will then allow you to pass the EMC on the first attempt. What I typically suggest doing is to write a test spec which would list all the electromagnetic compatibility standards that your product is intended to comply with, and then you could also send it to a test house to look at and explain to them what the operational environment for the product is going to be like, because they may actually come back to you and say that no, this is all wrong and you should do this and that, and that can significantly change your design process. Then after that, you should also think out of the box, literally. What kind of connections your product is going to have to the outside world? And is it going to use Ethernet cables? Is it going to use HDMI cables? And are you going to supply those cables with your product? Because if you are, it's very important that you follow the 360 degrees cable shielding rule as it is shown here, because if a cable shield of high-speed digital signal, let's assume, is not 360 degrees shielded and it contains gaps, then the electromagnetic energy will actually radiate through those gaps and it will become an antenna, such as the leaky feeder cable that is quite commonly used in tunnels and underground stations to provide Wi-Fi signals. So it's very important that any cable that you sell with your product is properly shielded, and it's a thick kind of shield that is not just a piece of tin foil, because like I said, magnetic fields tend to ignore those kind of shields that are very thin, and then the electromagnetic energy will exist around the cable and it will create electromagnetic waves all the same as if it was not there at all. Then for the next point, let's come back to the concept of wave impedance, and we can apply it likewise to the circuit, and we can call it circuit impedance. The trace impedance actually defines the ability of the lossless energy transfer between points A and B, and it does that in terms of so-called return loss, or otherwise called S11. And we can write return loss as S11 equal to impedance of the source minus impedance of the load, and divided over impedance of the source plus impedance of the load, like so. And the conventional value for source and load impedance in circuit board design is around 50 ohm for single-ended traces. So we can write it as ZS approximately equal to ZL approximately equal to 50 ohm for single-ended. And if that condition is satisfied, then that means that the energy transfer from the point A to point B will be completely lossless, and there will not be any electromagnetic interference to nearby devices, which is exactly what we're trying to avoid. For our friends across the lake, we can also express the same concept in terms of standing waves. And what standing waves are exactly that. They are mismatches between impedance in A and B, meaning that when the wave arrives to the point B and it is a bit too much energy, then this energy starts to bounce back and going back into the trace, and when the next wave comes in, it starts hitting it and creates a bit of interference. So the standing wave is defined as simply 1 plus S11 over 1 minus S11, and if you have it approximately equal to 1, then you have a very good impedance match. Whereas typically the value is around 1.2 to 1.5, indicates that this isn't a perfect match, but it's a close match. And if you have a standing wave of over 2, then you're really in trouble. Speaking of trouble, now what we assumed here is that there is a trace, but where is the wave actually propagating? Well, remember how I mentioned that a patch antenna is a dipole. And what happens in a dipole is that there are always two conductors. So there are electromagnetic waves propagate in a space between those two conductors. You have a patch on the top and you have a so-called ground reference on the bottom. And that is exactly what we typically need on our PCBs to ensure lossless energy transfer. So we can show it as this, where this is ground or otherwise 0 volt, and on the top is a trace, and now the electromagnetic wave is going to propagate inside the dielectric. And that is actually what happens all the time on circuit boards. So when people assume that the electromagnetic wave is propagating inside the trace, that is not at all true. In fact, electromagnetic waves propagate inside the dielectric on a FR4 substrate, which we are typically using for low-speed PCB designs. Now, moving forward, what would happen if I didn't have a continuous ground plane, but instead I had a bit of a plane here and a bit of a plane here, and there would be nothing in between? So this is not connected even. Then what's gonna happen? Well, first of all, your impedance match, you can forget all about it. It's not gonna happen, and instead the impedance will become completely randomized. So you're gonna have a lot of emissions happening. And this is why, if you watch any other electromagnetic channel on YouTube, you will hear the engineers telling you over and over again, use solid ground planes, use solid ground planes. And that is precisely why solid ground planes effectively ensure that you will have a good impedance match. So we talked about single-ended impedance so far, but we can also briefly talk about differential impedance. And the differential impedance is simply a type of impedance that occurs between two signals that are connected like so. So they are twisted pair in this example, which would be the case for Ethernet. And then the differential impedance would be the ratio between those two traces that accounts for the spacing between two traces and the width of those traces and the distance, like before, to the nearest coupling plane. So if we have it inside a PCB and we need a ground plane there, then effectively the differential impedance will be a ratio related to that. So we also need to ensure that differential impedance is the right value, and that could be 100 ohm for Ethernet or 90 ohm for USB, then 85 ohm for PCIe, and so on and so forth. Different standards require different differential impedance for the connections, and this has to be maintained across the solid ground plane as well. If you have any breaks in your ground plane, then this differential impedance is going to be screwed, and your signal integrity will be really bad. So far we've largely been talking about radiated emissions and how to deal with them, but we shouldn't forget about conducted emissions, or in other words, the emission that follows the wire. So if your product A is connected to a product B, it can easily transfer parts of its signal over the wire, and that will become noise to the other product. So that's what we typically refer to when we talk about conducted EMC, is the signal that, or noise, depending on how you look at it, that follows the wire, such as AC power cable that contains positive, neutral, or earth wires, and noise can travel on all of them. So when we look at it like this, we can really see that there are as many types of noise as there are types of signal, and there are different ways of dealing with them. So the most common ones are the differential mode noise and the common mode noise. So the differential mode is the one that travels on one conductor at a time, and so it will be opposite in phase on its return path. However, common mode noise travels on both conductors at the same time and in phase. So what it practically means is that we need to design some kind of a filter when we want to deal with those types of noise, and an example of such filter is an EMI filter that is typically placed on AC power input, and it contains components that help you to deal with both differential and common mode type of noise. You must also remember that filters never eliminate signal completely, they just attenuate it. So every filter that you design will have a specific noise attenuation, and an example of this one presented here, it's 60 dB per decade, which is pretty good, but you shouldn't be surprised when you see some of the noise still going through the filter and you being able to measure it. So if your source of noise is so strong, you may have to add multiple filters in series. When we talk about DC power, we also have the same problem pretty much, except instead of using EMI filter, we would typically use common mode filters and differential mode filters, as it is shown here. For example, for differential noise filtering, you may want to use ferrite beads on your power connectors and on your DC-DC regulators. Additionally, you may want to use capacitance and place them in close proximity to the source of noise, and you may also want to use common mode noise ferrite clamps or bypass capacitors to prevent the noise from traveling outside of your product. Then the last but not the least on my list today is providing protection from external events that may originate outside of your box. Remember to always think about outside of the box, and will potentially destroy the circuitry inside your equipment, and you should provide protection against them, again depending on your requirements, because for different environments you will have different requirements, and what goes well for commercial environment and domestic environment will not work well for railway environment, for example. But let's look at the most commonly used tools that will help you to deal with this type of transient phenomena. And the one that comes to mind straight away is the electrostatic discharge, which occurs naturally when we build up charge inside our bodies and touch electronic equipment. So the most common way of protecting your circuitry against electrostatic discharge is the addition of so-called transient voltage suppressor diodes, and those transient voltage suppressor diodes should be placed very carefully in path of the ESD source on any kind of external input or output where such a ESD spike could come from. So this is what's illustrated here when you often have situations where TVS is either not even there or it's on the other side of the board and it simply doesn't work. So what you really should aim for is the picture at the top here. Then whilst TVSs work really well for electrostatic discharge and fast transients, they don't always work too well for continuous or sustained surges. And in that case, we may want something a bit bulkier, and something a bit bulkier in this case would be a varistor, and that is a typically used component to clamp voltages on the mains input. If a long and continuous surge on mains doesn't go away immediately and it continues for up to 1 millisecond, a varistor can really take the damage and save your circuit. However, varistors will get burned and destroyed just as well, so for the best results you should provide a load dump circuit or a crowbar circuit to disconnect your mains in the event of a continuous overvoltage that is not going away and it just stays there. So the way the crowbar circuit works is that it will involve a resistor or SCR diode which will short out mains input to the ground and until the overvoltage condition is gone. So this type of circuit is really the key when you want to deal with automotive load dump tests and such. Finally, if you're designing something for medical grade or military grade that should also deal with voltage interruptions, then you really want to provide a secondary supply source such as a battery, and this is part of the voltage dips and interruptions testing, when you can have an additional circuit that switches on only when the voltage drops below a certain level and doesn't come back, obviously. So I think those are the main things that typically cause EMC failures in different environments. However, you, like I said, must be aware of what is the right environment for your product, and you should take ownership of the design process, and then and only then you can really pass the EMC first time when all of this comes together and you know exactly what you're doing. I hope you enjoyed this video. Please like and subscribe, and I'll see you in the next one really soon.